Hi, my name is Fredo Duran. I'm a professor at the Massachusetts Institute of Technology in Electrical Engineering and Computer Science, and my area of research is 3D computer graphics, as well as a new field called computational photography, where we develop new algorithms that allow us to extract more visual information from the world. For example, we just developed a technique that allows us to reveal very small changes that are invisible to the naked eye. Many scenes around us, like the ones portrayed in these videos, look static but contain very tiny variations, small motion and small color changes. We use computation to make them visible. We take a standard video as input, and for each pixel, we analyze the color variation over time. This is time. This is my color value. And if my input signal varies a tiny little bit like this, we amplify this variation, which gives us a much bigger variation for this pixel. Then we put the pixel back in the video, and we do this for every single pixel, which gives us the output video. In this example, it reveals the very small redness variation due to blood flowing through a face. With each heartbeat, blood is pumped to the face, which makes it a tiny little bit redder. This is usually invisible to the eyes, but our method can reveal it. Further, we can analyze the frequencies of the signal using a tool such as the Fourier transform, which for each frequency in hertz gives us the amount of energy in the signal. So in this case, it would be something like this, and typically there would be a big spike somewhere which can give us the heart rate of the person in beats per minute. We performed tests at a hospital, and the method proved as reliable as standard electronic heart monitors. The method can also reveal small motion, such as the pulsing of an artery. Even when they appear static, our eyes are constantly moving a tiny little bit, as revealed in this high-speed video processed using our technique. We can reveal tiny vibrations, such as those caused by the shutter of a camera while taking pictures, as shown here again using high-speed videos in our technique. Mechanical structures, such as this crane, sway in the wind, and we can make this a lot more visible using our computation. You can try it yourself, since we made our code available on the internet. In a different project, we downloaded a large number of photos from the internet of the same scene. These photos might have different viewpoints. They probably have different illuminations as well. We then register these images in 3D automatically, which means that we compute not only the 3D structure of the scene, but also the viewpoint of every single of the images. We then leverage the natural lighting variation as well as the correspondence between the images to decompose them into their illumination component and the intrinsic color of each object, regardless of the accidental illumination. We can then use the 3D structure that we have computed in order to provide much better interpolation between images, as you can see here. We can then use our decomposition into lighting and color in order to change the illumination in the input images. Now we make them all have the same illumination. This allows us to create 3D transitions where all the images have the same illumination. They are now synthetic images because the lighting was different when they were actually captured. We can also generate a synthetic time-lapse by varying the illumination of a given image by transferring the illumination from other images. We now show results on a different scene, a little village in Italy. See how the 3D structure we have computed makes for very seamless transitions, and you notice the 3D geometry of the scene. We can also transfer the illumination to generate new images where all the viewpoints have the same illumination, even though our input images have different illumination. We can also generate a synthetic time-lapse sequence. Only one of these images is a real image. All the other images have been synthetically generated by combining the illumination of one image with the reflectance of another image. We also work on the capture of 4-dimensional light fields. Wait, 4 dimensions? That's a lot of dimensions. What does it even mean to have 4 dimensions? We want to capture real scenes in the world in all their 3-dimensional glory. For this, we seek to record every single light ray that leaves the scene. And it turns out that light rays have 4 dimensions. You need 2 dimensions to encode their intersection with a given plane in 3D. And in addition to the intersection with the plane, you also need to encode the direction of the light ray as given by 2 angles. Here you go, you have 2 angles plus 2 dimensions on the plane. This is a 4-dimensional data structure. Now, how can we use a regular camera to record all these light rays? Well, I will let my grad student, A. Davis, tell you about it.
We present a new technique for capturing and rendering unstructured light fields with commodity hardware. To capture a light field with our technique, the user simply waves a handheld camera around the subject they wish to capture. As they do this, our system's user interface guides their motion of the camera towards undersampled parts of the light field, automatically recording new images whenever the camera is presented with a new perspective of the subject. To display the captured light fields, we present a new algorithm for rendering from unstructured sets of images that scales to larger data sets than previous techniques and produces fewer artifacts. This light field has 261 images and took just 2 minutes to capture. In addition to being inexpensive and easy to use, our technique is extremely robust. We consistently produce high-quality light fields for a large variety of scenes that are traditionally considered difficult, including human subjects and very specular objects. Here we show 4 outdoor light fields captured at different scales. Here we show 9 light fields, all captured with a simple web camera attached by USB to a laptop computer. This 842 image light field was the first light field captured by a user who had never tried our software before. At the time of this video, we have captured literally hundreds of light fields using our technique. Our system is cheap, easy to use, and it consistently produces compelling results. We hope that with our work, a much larger community of users will be able to capture light fields in the wild.
Let me say a few words about a class I teach at MIT. It's not offered yet on edX, but you can have a look at my webpage if you're interested. The class is about computational photography, and students learn algorithms that are involved in creating, editing, and enhancing images. All the programming is done in Python, so that means that you're already well equipped to do most of this work. In this class, we learn about high dynamic range imaging, which allows us to deal with difficult scenes like this one, where the contrast is way too high and parts of it are underexposed while other parts are overexposed. For this, we use multiple exposures. For example, we use an overexposed image, a normally exposed image, and an underexposed image. We then use an algorithm which we implement in Python. And you can see that it's not so much Python code. I'm sure you've implemented longer programs already. This code first merges all the exposures, and then it computes a tone mapping which outputs this image here where everything is nicely visible. We learn about panorama stitching, where we automatically compute the correspondences between images and stitch them together in a seamless wide-angle panorama. I teach non-photorealistic rendering, where we start from a normal photograph as input, and then we simulate brushstrokes using random number generators, pretty much the same you've used for Monte Carlo simulation. And then we obtain the following painterly rendering. We also implement morphing, which is a very useful technique if you need to transform a professor into a werewolf. The class is 6815, Computational Photography. It deals with many other exciting topics, and I hope you'll check it out. Thank you for watching today.